Today's topic is the basis functions or the basis sets. The basis sets or the basis functions has a form of the atomic orbital is linear combination with Gaussian G or Gaussian distribution function. The topic of the basis sets. I will show you the question of the what is a basis set. Why use the basis set? And solving the stationary state Schrödinger equation. How we use the basis set and the types of the basis set. What is a basis set? A basis set is a collection or set of the mathematical functions used to help to solve the Schrödinger equation. Each function is centered at some point in the molecule. Usually, but not always, the nuclei are used. In case of water, the center or the nuclei of the oxygen, hydrogen. The bases are at the nucleus of the oxygen and hydrogen. Each function is a function of the x, y, z coordinates of an electron. In the quantum chemistry, the basis set usually refer to the set of one-particle functions used to build molecular orbitals. Sometimes theorists might also refer to an electron basis set. This is something else entirely. Sets of Schroeder determinants. We design one or both of the following. The first, we get the electronic energy of the molecule. The second, the wave function for the molecule can be calculated as the properties of our molecule, such as dipole moment of the molecule, polarizability, electron density, spin density, chemical shifts, and so on. We satisfy our desire by solving the stationary state Schrödinger equation. We wish to solve the stationary state Schrödinger equation. Hamiltonian H acting on wave function psi equal to energy times wave function psi. The Hamiltonian H is nothing more than a mathematical recipe of operations to be applied to the wave function psi, such that we obtain a constant times and wave function psi back again after performing the prescribed operations. The constant will be the energy. In the Schrödinger equation. The only thing we know beforehand is the formula for Hamiltonian operator. The formula for Hamiltonian operator involves operations that apply only to the positions or coordinates of electrons and nuclei in the molecule. How we use the basis sets to solve the Schrödinger equation. Hamiltonian H acting on wave function psi to give the energy E. In order to meet our earlier desire, we must figure out what the wave function psi is, and then we can obtain the energy E. If we desire to solve the Schrödinger equation for any system with more than two particles, such as a nucleus and an electron, when we are forced to make guesses as to what the wave function psi is, the first guess is to use functions that are similar to the formula obtained already. This is functions like S, P, D, F orbitals, etc. of the atomic orbitals. Guess is to use basis sets, very loosely as sets of the functions like S, P, D, F orbital, etc. that will be used to describe the behavior of electrons in all systems, whether they be hydrogenic or not. The Schrödinger equation to obtain nice formulas of the wave function psi when we have an hydrogenic atom, such as the hydrogen atom, helium 1 ion, lithium 2 ion, and beryllium 2 ion. For the s orbital, this value we can get the answer as the exact value. The 1s orbital is equal to 2 square root of 1 over 4 pi multiplied with e power minus r. For solving the stationary state Schrödinger equation, equation 3.1, the Hamiltonian operator is known. For the wave function psi for the initial case, the energy must be consistent or self-consistency. We will obtain the energy E only if the wave function psi actually is the wave function. Otherwise, the H Hamiltonian acting on wave function psi is not equal to E on the wave function psi. Approximately solving the stationary state Schrödinger equation, equation 3.3. The Hamiltonian H acting on wave function capital psi equal to the exact energy E capital E letter times wave function psi. To calculate the exact energy, we use the Rayleigh ratio. But however, if we use the small psi wave function instead of the approximate capital psi, then we can show that the energy, the optimized energy small e, is equal to the integration of wave function small psi star h psi over the integration or space of small psi star times psi, as shown in equation 3.5. We can always find an energy small e this way. A theorem in quantum mechanics states that the small a is equal or smaller than the capital E if the wave function small psi is approximately equal to the capital psi. Then we can get the small energy, which is approximately equal to the exact energy. The use of basis sets in computation for optimized structure small e is as following description. The first basis sets are used to approximate the wave function small psi, which is a function of the linear combination with the atomic orbital psi r. The psi r obtained from the basis set as the atomic orbital is the function of the linear combination of the Gaussian distribution or the Gaussian functions. The second, the bigger and better the basis set, the closer we get better wave function small psi and optimized energy small e. The third, up to now, almost everyone utilizes the Gaussian functions as the basis sets. The fourth, one or more Gaussian type functions are used for each atomic orbital in each atom in the molecule of interest. Let's look at an example, the hydrogen atom, for which we already know what the wave function should be. We know that when we solve the Schrödinger equation for the hydrogen atom, we get as possible wave functions, such as the wave function is equal to 1s orbital, 2s orbital, 3s orbital, and 4s orbital, etc. And the lowest energy state is the wave function psi 0 is equal to 1s orbital. To resolve the energy is equal to minus half atomic unit or 13.6 electron volt. For the 1s orbital, we can get exactly the value as shown in the figure 3.6. The first excited state is the wave function psi 1 is equal to the 2s orbital. The 2s orbital can Get the exact value from the equation 3.7. Graphically, the 1s and 2s orbitals look like this figure. The red line belongs to 1s orbital, and the blue line is the 2s orbital. S basis functions. The exact S functions are of the form e power minus alpha rho. This form is used as accelerated form, where alpha is a constant. For the 1s of the hydrogen atom, alpha is equal to 1. Therefore, the 1s orbital is equal to 2 times square root 1 over 4 pi times e power minus r. For 2s orbital of hydrogen atom, alpha is a half. Therefore, 2s orbital is equal to square root 2 over 2 times square root 1 over 4 pi times 2 minus r times e minus r over 2. Gaussian basis functions don't even have the same form. S basis functions or GS value are the form of GS is equal to 2 alpha over pi power 3/4 multiplied with e minus alpha r square. Of course, alpha is again a constant. Contract Gaussians. A single Gaussian function is termed a primitive Gaussian can be improved upon. A basis function can, in general, be written as a linear combination of primitive Gaussians, as shown in equation 3.9. Atomic orbital size j is equal summation from I to n of dji multiplied with gij, where capital N is termed the degree of contraction. Dji are simple numbers called contraction coefficient. They are fixed for the basis set and do not vary in any calculation. The Gi are the primitive Gaussians and could be S, P, D, F orbital, and etc. Type Gaussian function. Types of basis sets. The first one is minimal basis set. Minimal basis set is smallest basis set. We may call it single zeta basis set. The second double zeta, triple zeta, and quadruple zeta, and etc. are the extended basis sets. This basis is used for the first and the second low atoms in periodic table. The third is spitz variant, and there are two special basis function, as one is the polarization functions, denoted as D, P. The diffuse functions denoted by plus sign. Minimal basis set. Only enough functions are used to describe the electrons of the neutral atoms, which is called pulse valence orbitals, also known as single zeta basis set. Zeta is the exponent used in the Slater type orbitals. The atom hydrogen and helium, they can have one s orbital or one atomic orbital. Atom lithium 2 neon can have one s, 2s, 2p, or 5 atomic orbitals. And atom sodium 2 argon can have 1s, 2s, 2p, 3s, and 3p, all 9 atomic orbitals. A minimal basis set is often represented by the notation STO-NG, the Slater type orbital. N is the number of primitive Gaussian, which denoted by G. N actually specifies the degree of contraction. RSTO3G basis set is commonly used. The basis set is used to calculate the atomic orbital Vj as the linear combination of the primitive Gaussian. This equation for the minimal basis set STO3G is reduced as the equation. This equation is V1 is equal to contract coefficient D11 times G11 plus D12 times G12 plus D13 times G13. The value of the contact coefficient are shown in the table. For the primitive Gaussian can be obtained using the exponent alpha ji. This figure is part of electron contribution according to the minimal STO3G basis set for the hydrogen atom. Using the 3 primitive, compare with the exact orbital 1s. The red line is the 1s exact orbital value. The blue line, the cyan line, and green line are the term of D11, G11, term D12, G12, and term D13, G13. If we combine the primitive terms, we can get this figure. The exact 1s atomic orbitals and STO3G basis function for the hydrogen atom. It showed the free-one orbital computed using the minimal SCO3G basis is in agreement with the 1s exact solution. The example for minimal basis set is TO3G for the hydrogen atom and carbon atom as the input of the calculation. For the hydrogen atom, as we mentioned on the previous slide, it shows that the atomic orbital free-one is the combination of the three primitive Gaussian. One, two, three primitive Gaussians, which are corresponding to the value in this table. The proposed basis sets were developed by the late Nobel laureate John Pope and popularized by the Gaussian set of programs. The SCO3G is a minimal basis set in which its atomic orbital is represented by three primitive Gaussians or 3G, chosen to mimic the behavior of STO. We call STO3G is the Pope form. Pope's speed valence double zeta basis set, called as 631G, is the core orbital is a CGTO made of the six primitive Gaussians, and the valence is described by two orbitals. One CGTO made of three Gaussians and one single Gaussian. The multiple zeta basis sets, such as double zeta, triple zeta, and quadruple zeta basis sets, double zeta basis sets double the number of the basis functions in a minimal basis set. For the hydrogen atom and helium atom are composed of 1s and 1s prime orbital, which become two atomic orbitals. For the atom of lithium, 2 neon, they consist of 1s and 1s prime, 2s and 2s prime, 2p and 1p prime, or 10 atomic orbitals are used. Inner and outer functions. The inner function has large zeta exponent and is tighter or closer to the nucleus. For the outer function has a small zeta, more diffuse, the further from the nucleus. Better description of the charge distribution compared to a minimal basis set can be shown on the examples of valence double zeta basis sets are the 3-2-1G basis set or the 6-3-1G basis set. The method of calculation can be HF/6-311G method. The FTBCLYP method using the 3-2-1G basis set. The method MP4 using the 6-311G basis set. An example of the valence triple theta basis set is 6-3-1-1G basis set. The split valence basis set. The first, only the valence part of the basis set is double. The second, core orbitals are represented by a minimal basis set. VDZ is the double zeta. It means time with two of the valence basis functions. For the hydrogen atom and helium atom, 1s and 1s prime, two atomic orbitals. This one is the same as the Z basis set. For the lithium and two neon atom, 1s, 2s, 2s prime, 2p, and 1p prime are used. 9 atomic orbitals. For the VTC triple zeta, quadruple zeta, quintuple zeta, and sextuple zeta, the valence basis function multiply with the 3, 4, 5, 6 respectively. The spectral functions. Polarization functions. Additional functions with higher angular momentum added to a basis set to allow additional angular flexibility. Molecules with strong local and global dipole moment. The orbitals for polarization of p orbital. P orbitals for polarization of s orbital. The diffuse function. Additional functions with very small exponents added to a basis set to allow diffusive electron behavior. Ions, dipole moment, polarizability, s orbital with very small exponents for diffusion of s orbital, p orbitals with very small exponents for diffuse of p orbitals. The effective core potentials denoted by ECP or pseudo potential using for many electrons atoms like metals. Normally apply to third and higher low elements. A potential replaces the core electrons in a calculation with an effective potential. eliminates the need for core basis functions, which usually require a large number of primitives to describe them, may be used to represent relativistic effects, which are largely confined to the core. For example, the method of PBE using the CEP121G ECP basis set. Some examples are CEP4G, CEP31G, CEP121G, LANL2MB, LANL2DC, and SHC basis sets. There are two good reasons to use ECP basis set. The first, a balanced basis requires a proper description of the core and valence region. For cesium atoms, there are a lot of core electrons as shown below. Most of the computational efforts is used to describe the energy, but not the valence region. The second, for the large nucleus, relativistic effects complicate matters.